Okay, so in this video I'm going to do the next part of the question in my last video. I did put a comment on that video, but I just wanted to highlight here that I worked out 5 children can stand at A before it tips, but the question asks how many children would be needed to tip the stone over. So obviously one more would have to stand on there to actually cause tipping, so 6 children would tip the stone, should be the final answer to that one. Okay, so the next part, we've got the stone's owner decides to move the support at C to a point nearer to A. To take the weight of the slab while doing this, he sets up the lever system shown in the diagram. The distance xf is 1.25 metres and fy is 0.25 metres. What downward force applied at x would reduce the reaction force at C to 0 and so allow the support to be moved? Okay, so we've got a reaction force at C, a reaction force at D. We've got the weight as before, 0.3 metres from there, 1 metre from there as we said above, so let's mark that one as well. Okay, that was 1.2 metres and that was 0.5 metres. Okay, so now we've got, and we've also got, we're just going to look here at the slab first. So these forces, and we've also got a force here from the lever. So there's going to be a reaction force upwards from Y. So let's call that RY, a force acting upwards there. Okay, so we want the situation in which RC is equal to 0. So I think it would make most sense to take moments about D, because that's going to be 0, and then we don't need to worry about this. We want to find out what effect the lever is having. So we want to find out RY over here. So let's take moments about D. Let's start with clockwise. So what is going to have a clockwise effect? Well, RY is going to have a clockwise effect, and that's going to be multiplied by 2.5. That's the total distance there. And then the only other force, that's going to be 0, so we don't need to worry about that one. Then there's going to be a negative, so an anti-clockwise moment from the weight of the stone itself, so that's 1000 G times 1, okay? And it's still going to be in equilibrium, so that's going to equal 0. So we want to solve that for RY, so we're going to get RY is equal to 1000 G divided by 2.5, which is 400 G. Because I'm going to do some more work with this, I'm going to leave it in terms of G, so I don't introduce any sort of rounding errors or anything like that. So RY is 400 G. So now what I want to do is think about the lever, what's happening at the lever. So let's draw a smaller diagram over here just of the lever itself. So we've just got this, X, Y, and we've got the F there. Now if at the point Y the lever is pushing up on the slab, then at that point the slab is pushing back down with the same magnitude on the lever. Okay, that's Newton's third law there. Okay, so the lever is pushing up on the slab with 400 G newtons, so that means that the slab is pushing back down on the lever with 400 G newtons at that point. Okay, distance is on 0.25 meters here and 1.25 meters here. Then we know there is a force here. Okay, let's call, well, we might as well call that force X, as it's at the point X. Okay, we're pushing down with that force, we want to work out how big that is. And of course there will be a reaction force here at F, and we're going to assume that the lever is light. Okay, the lever is light, so it doesn't have any of its own weight. So now on the lever we're going to take moments about F to work out what that downward force would have to be. Okay, so what's going clockwise about F? This 400 G times 0.25. and anti-clockwise we've got x times 1.25. Okay, and the system is in equilibrium, so that's going to equal 0. So now solving for x, we are going to end up with x equals 400g times 0.25, so 100g divided by 1.25, which is 80g, which is 784, or roughly 784 newtons. So that's the force that's needed to push down on the lever to reduce the to get rid of the reaction force at C and move the support.